Our next example involves infant mortality rate. The infant mortality rate is the number of deaths of infants under 1 year old per 1,000 births. In 1915, the rate was almost 100 deaths per 1,000 infants, or 1 death per 10 infants. The infant mortality rate has decreased substantially since then. See Table 45 on page 294 of our textbook, where it lists the infant mortality rate for various years. Our directions ask us to use the data points from 1940 and 2010 to find an exponential model for the infant mortality rate. In 1940, the mortality rate was about 47.0 deaths per 1,000 infants. And in 2010, the mortality rate was about 6.2 deaths per 1,000 infants. Now, there's a lot of ways we can set this up. You can choose whatever you want to be your starting year. I tend to find it easiest to take the year of my first data point and let that be my starting year. Some people like to choose a nice round number like, say, 1900 in this case to be their starting year. But I'm going to choose 1940 to be my year 0. That means that for 2010, I would take 2010 minus 1940, and that is 70 years after my starting year. So the X value that I'm going to use when finding my formula for 2010 would be 70. So here we have the point 0, 70. 0, 47.0, because in our starting year, the mortality rate was 47.0, and 70 years later, the mortality rate was 6.2. So those are the data points we're given, and we need to find an exponential model for that mortality rate. Remember, that means we're looking for something of the form y equals a times b to the x. And because we set up 1940 to be our starting year, we already know where the starting value goes. We already know that a would be 47. So here we will have y equals 47 times b to the x. And now we're going to use our other data point to figure out what b is. We're going to put in 70 for x and 6.2 for y. Here we would have 6.2 equals 47 times b raised to the 70th. So to solve this equation, our next step is to divide both sides by 47, giving us 6.2 over 47 equals, and I'll leave just a little bit of space, b to the 70th. And now to get that b by itself, we need to get rid of the 70 exponent. We would take the 70th root of both sides. The way the equation is set up right now, we don't need to take a logarithm. You take a logarithm of both sides when you have a variable in the exponent. When you have a number in the exponent, that number tells you what root to take of both sides. So when we calculate this, the 70th root of 6.2 over 47, here's something important is you don't want to round your answer off too much. Rounding your answer off to 1 or 2 decimal places when you're dealing with rates can throw things off quite a bit. If you are going to round, I would go out to about 5 decimal places or so. So here I would put b as about 0.97148. That's rounding the result that I get off to 5 decimal places. So I can say the model that I need is y equals 47 times 0.97148 raised to the x. So our next question, keeping that model in mind, it says, what is the percent rate of decay for infant mortality rates? Now remember, our multiplier is 1 plus or minus our percent rate change. So here we can say 1 minus that percent rate is 0.97148. Or another way of saying it is our rate is 1 minus 0.97148. If we calculate that, 1 minus 0.97148, we would have that R is about 0.02852. That's a decimal. To put it in percent form, we would move the decimal point over 2 spots, and it's about a 2.852% rate of decay. If we look at our last question, it says, find the year when the infant mortality rate will be 4.7 deaths per 1,000 infants. So here we're going to take the formula that we came up with and put in 4.7 for y. This gives us 4.7 equals 47 times 0.97148 raised to the x. And we're going to solve for x. To do that, first, we divide both sides by 47. 4.7 divided by 47 turns out to be a nice number to work with. If you get a really long decimal, I tend to just leave it as a fraction. But here, 4.7 divided by 47 is just 0.1. So we have 0.1 equals, and I'll leave some space, 0.97148 raised to the x. Then we take a logarithm of both sides, and that allows us on the right side to pull the x out to the front. We would have the logarithm of 0.1 equals x times the logarithm of 0.97148. And then we divide both sides by the logarithm of that decimal to get x by itself. And here, when we calculate the value of that left side, the logarithm of 0.1 divided by the logarithm of 0.97148. Here we end up with about 79.57. And since we're going to need to find a year, we'll go ahead and round that off to the nearest whole number and say that it is about 80. Since it's asking for a year, recall that we set up our starting year for this problem to be 1940. So we would take 1940 plus 80, and our result is that we're looking for the year 2020.